Ever wondered what's really going on physically during a collision? From a tiny little tap to a huge crash, there's a core principle that governs it all. Well, today we're going to break down the physics behind every single push, bump, and impact. Let's dive in. Okay, so think about bumper cars. We've all been there, right? That jolt you feel when you smack into another car? Well, that's not just random chaos. No way. It's actually a perfect real-world example of two fundamental ideas in physics, impulse and momentum. And trust me, by the end of this, you'll see exactly what's happening under the hood. All right, so first up, let's talk about momentum. Honestly, the easiest way to think about it is as an object's oomph. You could also call it its unstoppability. It's not just about speed, it's about how much that thing wants to just keep on going. And you know what's wild? The official physics definition is incredibly simple. Linear momentum, which we call L, is just the object's mass times its velocity. That's literally it. This means a heavy truck moving kinda slow can have way more oomph than a super fast baseball. And since velocity has a direction, guess what? So does momentum. And of course, you see this all over the place in sports. I mean, the entire goal of swinging a golf club is to transfer all its momentum into that little ball. It's the same thing with a tennis ball machine. Those wheels are spinning with momentum, and they just hand it right over to the ball, sending it flying. Really, most sports are just a game of strategically moving momentum around. Okay, so if momentum is the oomph, then what actually changes it, right? That brings us to our second big idea, impulse. And if momentum is the oomph, then you can think of impulse as the kick. It's the specific action that changes an object's momentum. Now here's the crucial thing to get. Impulse isn't just about how strong the force is. It's the force multiplied by how long that force is applied. So a massive force that acts for just a millisecond can give the exact same kick as a much smaller force that acts for a whole second. It's both the force and the time that matter. If you're a visual person, check this out. It's a great way to see it. If you plot force over time on a graph, the impulse is simply the total area underneath that curve. If the force is steady, it's just a nice simple rectangle. But if the force changes, like a bat hitting a ball, it's a more complicated shape, but the principle is exactly the same. And here's a fantastic real-world example. This dent puller is all about impulse. It works by creating this massive force over an incredibly short period of time, right when that sliding weight slams into the stop ring. That sharp, sudden jerk is a huge impulse, and that's what's strong enough to yank the metal back into shape. Okay, so we've got our two big players, momentum, the oomph, and impulse, the kick. Now it's time to put them together. This is where the magic happens, the central idea that makes all of this so incredibly useful. And there's a reason physicists get so excited about this. It's basically a physics shortcut. Instead of having to calculate acceleration first and then figuring out velocity from that, this principle lets you connect the forces acting over time directly to the change in velocity. It's just one step. Super efficient. I love this diagram because it tells the whole story in three simple parts. On the left, you've got the object's initial momentum. That's where you start. In the middle, you've got all the impulses, all the kicks it receives. And then on the right, you have the final momentum. That's where you end up. It's really just a story of cause and effect. So let's just boil it down. 1, an object is cruising along with its initial momentum. 2, it gets a kick. That's the impulse, a force applied over some amount of time. 3, it now has a new final momentum. Start, kick, end. That's it. That's the whole principle of impulse and momentum right there. But what happens in a special situation where there's no external kick? When all the pushing and pulling is happening inside a closed system. Well, this leads to one of the most powerful and fundamental laws in all of science. So let's think about that for a second. What if you have a system of objects that's totally isolated from the outside world? If the only forces are the ones they're putting on each other, what happens to the system's total oomph? The answer? Absolutely nothing. The total momentum is conserved. It doesn't change one bit. Now, it might get shuffled around between the objects inside, but the total amount you started with is the exact same amount you end with. And this isn't some kind of magic. It comes directly from Newton's third law. For every internal action, there's an equal and opposite reaction. So all those internal forces just cancel each other out, meaning the total momentum has to stay the same. This is exactly what's happening with our bumper cars, and you can see it perfectly here with these two boxcars. When they smash into each other, that coupling force is enormous. But it's an internal force. It's just between car A and car B. As long as there are no major external forces, like friction, the total momentum of that two-car system is conserved right through the collision. And the math just backs this up beautifully. You just add up the momentum of each car before they hit, and that total has to equal the final momentum of the two combined cars after they're stuck together. It's such an elegant and powerful calculation. Okay, so to really use this stuff like a pro in the real world, you've got to learn a key skill. You need to know which forces are the main actors in a collision and which ones are basically just background noise. And that's the difference between impulsive and non-impulsive forces. Impulsive forces are the superstars of the show. They're the massive, short-acting forces of the impact itself. Then you have the non-impulsive forces, like gravity or weight. They're still there, sure, but during the split second of a collision, their effect is so tiny in comparison that we can pretty much just ignore them. I mean, just look at this picture. It says it all. The insane force from the racket that's deforming that tennis ball, that is an impulsive force. But during that tiny fraction of a second, the pull of gravity on the ball, it's completely non-impulsive. It has almost zero effect on the change in momentum during the hit, so for our analysis, we can just pretend it's not even there.
All right, let's bring it all home. Think of this as your new physics toolkit. Number 1, momentum is an object's oomph, its quantity of motion. 2, impulse is the kick, that force over time that changes the oomph. 3, the core relationship is simple. Initial momentum plus the impulse equals the final momentum. And finally, number 4, if a system has no external kicks, its total momentum is always conserved.
So there you have it. You're now equipped to see all these interactions happening everywhere. Seriously, think about it. A game of pool, a fender bender, even just clapping your hands. The world is just filled with impulse and momentum. So the question I have for you is, what collision will you never look at the same way again?